Yeah, all right. Well, first of all, thank you to the organizers. This has been a really nice conference so far. Yeah, I'm Natasha. I'm a postdoc in Paul Warburton's group, UCL, and I'm going to be talking about some of the work we've been doing looking at algorithmic catalyst construction. And I feel like we're getting some feedback, but I'm just going to keep going. Is one of those mics on or something?
Maybe you can try with these ones.
Okay, great. Yeah, so to give a quick outline of what I'm going to talk about, I'm going to start by giving a quick introduction to the use of catalysts and quantum annealing. I'm then going to kind of go through the theoretical background of perturbative crossings, which is the problem of the bottleneck that we're going to be focusing on in our work. I'm also going to get some water, I'm sorry. I'll then go through some example instances, so showing that the catalysts that we're looking at do perform as we want them to. And that's kind of all stuff that I have to varying degrees presented on before, but the new stuff that I want to talk about today is kind of the idea of like taking these ideas of a targeted catalyst and seeing if we can build it into a sort of recursive algorithmic approach to building catalysts in quantum annealing. So it's now day 3 of the conference. I think I probably don't need to go through how quantum annealing works, so I'll just draw attention to the kind of particular element that is relevant to this, which is that when we have these small gaps appearing in the annealing spectrum associated with the evolution from our driver to our problem Hamiltonian, we can end up leaving the ground state if we run our anneal too quickly. And this is a problem because often these gaps close exponentially with the problem size, and then we have an exponential time scaling as well. So the basic idea behind a catalyst is to just change the path that we take between the driver and the problem, thereby changing the associated gap spectrum and potentially enhancing the gap minimum. So one particular cause of exponentially closing gaps are perturbative crossings, and we can understand these by looking at the lowest lying excited states and introducing the driver as a perturbation to these states. And when we do this, we can expect that potentially some of the excited states that are very close in energy to the ground state may end up crossing the ground state. And where we have that, we can expect a small gap minimum to appear in the annealing spectrum, where the finite gap size is a result of tunneling between the states. So to kind of give some idea of when we can expect these to form, we can show using perturbation theory that states corresponding to the global and local optima will receive negative perturbations from the driver. And we can also show that states that are coupled by the driver to more low energy states will receive larger perturbations, and therefore be the states that are likely to cross the ground state and create these perturbative crossings. And we can kind of just think of that as the algorithm being more likely to get caught in local optima that are at the bottom of like wide potential wells. So in terms of what we would want from a catalyst to try and remove these, we would either want to, say, increase the negative perturbations to the ground state, or maybe introduce positive perturbations to the excited state to try and pull these states apart and remove the crossing. So then the question is, how can we pick our catalyst to achieve this? So the catalysts that we've been looking at are XX, basically taking some subset of potential XX couplings between vertices. Rupayan also was talking about this earlier on Monday, sort of related but a slightly different approach to trying to pick your catalyst terms, and also looking at higher order terms, of course. For this talk, I'm just going to be focusing on 2 local XX. And again, using perturbation theory, what you can show is basically your options are to introduce XX terms with the same sign as the driver that couple the ground state to other low energy states if you want to sort of lower the energy of your ground state and remove your crossing like this. Or the other option is to introduce XX terms with the opposite sign to the driver that couple the excited state to other low energy states, so sort of the reverse approach. And that is the approach that I'm going to be focusing on in this talk. All right, so now we can go through some example instances to kind of show that the catalysts that are designed in this way do what we're expecting them to do. So just for formality, here is our annealing Hamiltonian, where S is a parameter that we vary from 0 to 1, so that we start in our driver, transition to our problem, and along the way we have this catalyst Hamiltonian. And for our driver, we'll just be using the standard homogeneous local X field across all the spins. Our catalyst, again, is this sort of like subset of potential XX couplings that we could use. And then our problem Hamiltonian is obviously the Ising Hamiltonian, so just local Zs and then ZZ couplings. The problems that we're going to be looking at are maximum weighted independent set problems. There's not really a specific reason to use this problem in terms of the actual problem it is, although it is NP hard. But it's a very good tool for creating this sort of spectra that we want to test these catalysts on. Because the kind of like crucial bit for that is actually the problem like eigenspectrum and the structure in that. And what's nice about the max-weighted independent set problems is that the local optima here are, of course, the different maximally independent sets, and the size of the dependent sets, or independent sets, sorry, control the widths of the potential wells of the different local optima. So we can basically quite controllably and quite nicely create these settings with perturbative crossings that we want. So for the first example, I'm going to be looking at this bipartite graph that has come up a few times. So our global optimum here is the blue vertices, the weights are chosen, so that's the global optimum. And the local optimum is the orange vertices. And because it has more vertices, we're going to expect this perturbative crossing to form. And here you can see the associated gap spectrum, and we see that we do get that small gap minimum towards the end. So then what we want to do is introduce our catalyst to do what we said before, so couple the excited state responsible for the perturbative crossing to other low energy states. And in the max-weighted independent set problem, the way we want to do this is to introduce couplings between the associated vertices, so like this. And looking at the gap spectrum, we can see that we do get some nice gap enhancement doing that. But potentially more interesting than gap enhancement for a single instance is improvement to the gap scaling. So we can scale this graph up very easily by simply adding vertices to the two sets. In black here, we have the gap scaling without the catalyst. You can see kind of closing exponentially. And then in purple, the gap scaling with the catalyst introduced. And what you can't see very well, which is good news, of course, is the dashed gray line underneath the purple line. And that's the gap scaling of the gap at the end of the anneal, which is purely dependent on the problem, and so the maximum gap enhancement that you could achieve. And we can see the catalyst is doing that. But generally, you would expect in kind of like an interesting problem setting for there to be multiple perturbative crossings from different local optima. So here is the case where we have a single perturbative crossing that we're removing. But we can also have a look and see that the catalyst is able to remove multiple perturbative crossings from the same instance. So here we have an example where we have two local optima that create perturbative crossings. At the top, we have the gap spectrum, and below, just a cartoon that's going to hopefully help illustrate sort of what's going on here. So you can see we have this gap minimum, and that's associated with this first perturbative crossing that you can see. And so what we want to do is we want to introduce our XX couplings to couple the excited state responsible for that perturbative crossing to other low energy states. And again, we do that by adding XX within or between the couplings, between the vertices, sorry, associated with that local optimum. And doing that, you can see we have a change to the problem spectrum, but we still have a gap minimum associated with the remaining perturbative crossing. So then we can do the same for that remaining local optimum, and you can see that by doing that, we are able to get significant gap enhancement. But then the question is, how can we identify suitable couplings? Because, of course, if we have to know the structure of our problem to pick our couplings, that's not a particularly useful catalyst to use in practice. But what's nice is that there's actually good reason to expect that the measurements that we would perform would give us the information we need to construct our catalyst. So kind of to explain that a little bit, if we are expecting most of the state transfer to happen at these perturbative crossings, we can imagine that if we run our anneal initially, we are quite likely to have the anneal return the local optimum that is responsible for that first perturbative crossing. allowing us to pick our XX couplings appropriately. And then similarly next, we're likely to return exactly the next local optimum that is responsible for the remaining perturbative crossing. And so this was sort of the inspiration behind the idea of, well, maybe you could do this sort of recursively and use your measurements to guide your catalyst construction. And yeah, that is what I'm going to talk about now. So obviously, to start, we obviously don't have XX couplings in our annealer right now. I mean, Paul gave a nice talk sort of talking about how we might try and do this. For the sake of what I'm going to talk about here, I'm going to assume we will hopefully one day have access to XX couplings that we can introduce. Of course, everything I'm going to present now is simulation. But the idea behind sort of an algorithmic approach would be to say, start with your catalyst-free Hamiltonian, run your anneal a certain number of times, pick the lowest energy state that you measure. If that's not a local optimum, you can just do gradient descent, something simple to get to a local optimum, and then pick your couplings and your catalyst according to that local optimum that you've obtained. Update your catalyst, repeat the process, and then do that for some number of times or until some termination condition is met. So maybe you want a solution of a certain quality. Obviously, the sort of meat of this is in step 5 in terms of what we're talking about. And to recap, what we want to do is couple whatever local optimum we obtain to other low energy states. For the max weighted independent set problem, again, this is very straightforward. We can just pick vertices that are in that local optimum. More generally, you could potentially just calculate the energies of the different states that are 2 spin flips apart from the local optimum you found. That's not something where the complexity scales exponentially, so you could do that, or there might be some other trick for a particular problem that you want to solve. Again, of course, this is all going to be simulation, so in testing this, what we're going to do is to just simulate the closed system dynamics, and then doing that, we get some state that is some superposition of all the different problem states, and then we can sample that to get our measurements. In terms of comparing to standard quantum annealing, the thing that we're going to do is for some set of test instances, which I'm going to talk about briefly in a moment, basically run this process, run this kind of algorithm 100 times per instance, and then at each step of the algorithm, we can look at the percentage of times the ground state was measured by that step and treat that as our success probability at that step. And then what we compare that to is the success probability after the equivalent number of catalyst-free annealing runs. Because obviously, if we just repeat our measurements, our probability of measuring the ground state is going to increase whether or not we update our catalyst. So that's what we're going to compare to. Probably the trickiest part of this whole process, or this whole project, was trying to find instances to test on, because obviously we need to be able to simulate them. They need to be small enough to simulate, but it's quite tricky to get actually difficult instances of that size. If you randomly generate them, you don't tend to get anything that is actually that difficult for annealing with these different perturbative crossings. And if you do, you tend to have, say, maybe one perturbative crossing, and we're really looking for instances where we can see if we can remove multiple from the same problem. So what we've done, our test instances are 18-spin instances where we've effectively seeded local optima quite deliberately into them. And I won't go into too much detail about that, except to say that obviously, we've talked a lot about these sort of different toy instances that are all these n-par-type graphs. These are a little bit more complicated and interesting. You can get sort of overlapping local optima, so they're just a little more expressive and give us a few more examples to test on. Okay, so I'm now going to move on to the numerical results, and these were done by Sebastian, who is somewhere here. Thank you, Sebastian. I'll first talk you through what we're seeing here. So what I'm showing you here is each of these crosses is corresponding to a single problem instance. Then up the y-axis, we have the sort of probability of our algorithm finding the ground state by a certain step. This is step 1. And then the probability of just like running the anneal with your unmodified Hamiltonian. Here at step 1, these should in theory be all lying along the diagonal, but of course with our algorithm that's a statistical procedure, so you can see some are a little above, some are a bit below. And so what I'm going to do now is so basically like flick through these steps. And what we're hopefully going to see, and spoiler alert, this is what we see, is we want these crosses to move up so that we can see that the algorithm is guiding us towards the ground state more effectively. So yeah, flicking through, you can see that we do indeed get this improvement using the algorithm of these crosses all moving up towards the top of the plot. You can see basically by updating our catalyst each step, we are able to get a lot of these very close to unity. And for me, I mean, the really nice news is these crosses obviously towards the very left of the plot, where even at this point, after these repeated measurements, we're still getting, if we're not modifying our catalyst, a very close to 0 success probability. And with the catalyst, we can see that we're pushing that up towards unity. Yeah, so these are obviously still very initial results, not that many problem instances, but we think they look very promising. And so this is kind of what we're going to continue to look at. I'm not sure where I am time-wise, but OK, perfect. The last thing I want to talk about is the idea of how crucial are the coupling locations, because obviously each step we're adding XX terms, new XX terms to the catalyst, but maybe it's just good to add XX terms into your catalyst. So we just kind of wanted to confirm that actually it is important that we're doing this process of figuring out where to put them. So to do that, we basically looked at what happened if you start changing the couplings away from where this algorithmic approach has sort of led you to put them. So this is just for one example instance. And on the y-axis, we have the final ground state overlap when that catalyst is used. And then on the x-axis, we have how many couplings we're changing. So the 0 is just the catalyst that was obtained by kind of doing this algorithmic approach. And you can see it's got a pretty high ground state fidelity. And then if we move 1 across, we've got a randomly generated set of catalysts where one of the couplings has been moved. And we can see that some of them still do fairly well, but we get this drop-off. And then as we change more and more, moving to the right of the plot, you can see that we get this drop-off in the fidelity. So it's with the same number of couplings, but just in a different location. And this example catalyst had 6 couplings in it. And you can see at the very right of the plot, by the time we've moved all of them off from where they were initially, we get basically 0 fidelity. So it's clear that the coupling locations are important. And yeah, this is the sort of plot you see for the other example instances as well. So yeah, to summarize, we have sort of motivated these targeted XX catalysts that can be used to remove perturbative crossings to hopefully get these faster routes to the ground state. We've kind of introduced the idea that hopefully we can use information obtained from what you might call failed annealing runs to actually pick what couplings you want to use. And then, yeah, we've sort of started testing this as an algorithmic approach, and I think the initial results look very promising. But of course, there's still a lot we want to do. We'd love to move to sort of more general max-weighted independent set problems, also applying this to other problem settings, and just confirming how it does there. And then also kind of trying to refine this process. There's a lot of parameters that you could tune in the algorithm that we haven't had a proper play with yet. But yeah, with that, thank you all for your attention, and have some questions.
OK, thank you very much. Questions? Over there.
Thank you for this very nice talk. So I have a question. So imagine that you want to apply this technique for a problem which is kind of hard fundamentally, and that a catalyst will not solve, will not work, no, will not help. How this kind of fundamentally impossibility of solving your problem, no, will manifest with your algorithm. So when you realize that, okay, the technique is not working, no, how you see that?
So if I've understood the question correctly, you're asking, so if we try and update our catalyst using this method and it's not working, what's the next approach? Did I understand that?
Well, because I was so I understand, no, that in this iterative approach, no, you start to kind of turn on XX interactions, no,
Mm-hmm. Yeah.
and then okay, imagine that. So okay, the answer I was expecting was like, okay, you see that, okay, you increase one gap, no, but you still the gap remains low, no, and at some point then you see a gap that you cannot increase, no, and then this is how you see that the technique is not kind of working, and then you explore all the possible XX couplers, and once you see that this doesn't vanish, then you assume that the method no longer works, or this is how it...
I mean, yes, I think is the simple answer to that. Generally, in what we've looked at so far, you are able to end up opening the gaps, but I'm very happy to say, of course, that we've definitely not exhausted all the potential like settings and complexities and different things you might see. But so far, it has generally opened up. I think there's been like a couple of instances where it has not, and the specific quality of those instances are these like very odd cases where the local optimum that was creating it was like very, very tiny and somehow still causing a problem. But I think before we did these 18 spin instances, we did slightly smaller instances and about 140 of them. And I think there was only like one instance in that set where the gap was only a bit enhanced. Generally, it was able to get rid of these small gaps.
Okay, thank you.
Okay, more questions? Okay, over there.
So you said that you chose the MWIS because the independent sets are the local minima, and the number of those control the size of the local minimas or something like that.
Yes, it's basically the local minima, which are the independent sets. When those are very large, that basically means they're kind of sat at the bottom of a very large potential well, and it is more likely to make these.
Okay.
Yeah.
And is that property important while you use this method? So is that property essential to basically do this technique to enhance the gap?
So I definitely wouldn't want to confidently say this will definitely work for everything. Like, we very much need to test it numerically. What I will say is that like all the theoretical arguments for why this should work have nothing to do with the specific structure of the max-weighted independent set problem. They're all to do with sort of the connections between eigenstates in the problem spectrum, which should be more general and apply to other settings as well.
Okay, thanks.
Okay, another question?
Thanks for the nice talk. So, like, perturbative crossings, if I understand correctly, are at the end of annealing, right? So they are basically almost like classical states plus corrections.
Yeah.
Sometimes during quantum annealing, you have phase transitions happening also earlier, like ferro to para phase transitions, or even any sort of exponential or super exponential gap closures during the annealing for whatever reasons. Do you think this approach can also be applied in those cases, or is it specific to the perturbative crossings?
I'm going to say, for the sake of not being misleading, I think this is probably specific to perturbative crossings. At least that's where all the kind of like theoretical backing comes from. The only caveat I will say to that is quite a few years ago now, I was trying to have a play with like small versions of the like p-spin model, where like there you have this first order phase transition going from like your paramagnetic phase to the phase you have at the end. And that's not really described as a perturbative crossing, but kind of taking a similar approach and which couplings to put in. You could basically do the same thing with the maths, and then simulating it kind of had a similar effect. So I think there's like a bit of a gray area where, like, depending on what you're willing to, you know, a perturbative crossing is not like a very fixed, there's no fixed cutoff of like when it happens, and I don't know. This is a very vague answer. I will say that this technique is like specifically for perturbative crossings, but it wouldn't surprise me if it was kind of generally helpful if you took
sure.
this
Just
approach.
a quick follow-up, if I may. So, is there any reason why in maximum weighted independent sets you expect to have only perturbative crossings rather than other kind of phase transitions? So like for p-spin, for instance, since it's integrable, you know what is going to happen. I mean, you even know, I think, the point where the phase transition occurs. But this is actually an NP-hard problem. So is it like known that you are going to have, or at least like in your simulations, do you always see perturbative crossings towards the end of annealing rather than, let's say, other closures before or even both of them?
I will say that all the kind of gap closures we see when we do these problems are at the end of the anneal and appear to be perturbative crossings, but also these are very small problem instances. And so, like, unless you're really forcing it through the structure of the problem, you don't really see any small gap minima. So it is like potentially, like if you were to scale up to much larger problem setting, perhaps there are hidden other gap closures that might be happening. But certainly at this scale, we don't see any other small gaps forming in these problems.
Thank you.
Okay, I think we can thank again Natasha. And